In this video, we will be discussing the concept relation. Relation and functions are two important concepts in mathematics, widely used in many branches like calculus, algebra. These concepts are introduced to us by the great German mathematician Leibniz. He is one of the founder of calculus. Another person who developed calculus is Isaac Newton. They developed calculus independently. Both of them have used the concepts like relations, functions, etc. in calculus. Now, relation you can see in our daily life. For example, father-mother relation, father-son relation, husband and wife relation, brother-sister relation. Likewise, you can see relation from a set of persons to another set of persons. In the field of numbers, we can say m is relatively prime to n, suppose, then m and n are related. If two numbers a and b are such that a is less than b, then a and b are related. If two numbers x and y are equal, then x and y are related. Such kind of relationship you can see in the field of numbers. So in geometry, suppose there are two lines L1 and L2 which are parallel, then we can say in some way L1 is related to L2. If two lines are perpendicular, say M1 and M2 are two lines which are perpendicular, then M1 is related to M2. If you take any subsets A and B, if you take such that A is a subset of B, then A is related to B in some way. These kinds of relations are discussed in this chapter in detail. In all these kinds of relations, association from an element to another element involves a pair of elements, a pair of objects, a pair like L1, L2. The set of all such pairs, especially this is called ordered pairs, where L1, that is first object coming from a set, the second object coming from another set. Such a set of all ordered pairs we term actually by Cartesian product. We will be discussing first Cartesian product before going to the concept of relation. Now we'll see what is Cartesian product. Cartesian product of two sets first. Suppose A and B are any two non-empty sets. Then the Cartesian product of A and B is denoted by A cross B, which consists of all the ordered pairs xy, where x is from A, y is from B. Let us illustrate with an example. Suppose A is equal to set 1, 2, 3 and B equal to set A, B. Then A cross B is the set of all pairs, possible pairs. What are the possible ordered pairs? If A has 1, 2, 3 as elements and B has A, B as elements. Now the possible pairs are 1A. That is, when you are writing A cross B, you have to write the pairs such that the first element x coming from A and the second element coming from B. So write 1A is there, 1B is there. So it consists of pairs like 1A, 1B, then 2A, 2B, 2A, 2B, then 3A, 3B, 3A, 3B. So here A has 3 elements, B has 2 elements, and you see how many elements are there in A cross B? 1, 2, 3, 4, 5, 6. So here number of A is 3, number of B is equal to 2, and we got number of A cross B is 6. Now do these have some relations? Let us verify with taking one more example. Suppose P equal to set 1, 2, 3, 4, Q equal to set A, comma B, comma C. Then try to write P cross Q. So P cross Q consists of all the pairs 1A, 1B, 1C. So 1A, 1B, 1C. Then starting with 2, 2A, 2B, 2C. Then with 3, 3A, 3B, 3C. Then finally with 4, 4A, 4B, 4C. So these are the pairs. So 4, 4, 4, 4 into 3. That is 12 elements are there. Now you see here number of P equal to 4, number of Q is equal to 3. So number of P cross Q is equal to 4 into 3, that is 12. So we are getting a relation. Number of P cross Q, P and Q are in two sets. Number of P cross Q is number of P into number of Q. So if A has m elements, B has n elements, then A cross B will have mn elements. Next, what will be A cross A? That is a cross product of A with itself. Suppose A is equal to 1, 2, 3. Then to write A cross A, you have to write A one more time, 1, 2, 3, the same set. Then you write all the possible pairs A cross A, which consist of pairs like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. 1, 1, 1, 2, 1, 3, etc. 3, 1, 3, 2, 3, 3. How many pairs will be there? 9. So number of A cross A equal to 9, which is number of A into number of A, that is 3 into 3, which is 3 square, that is 9 elements. This A cross A, in short form we will write A square. In set theory, we write A cross A is equal as A square. In a similar way, you can define A cross A also. This consists of all the triplets X, Y, Z, where X, Y, Z in A. All the triplets, that is 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3, like that. You write all the pairs. You can see that number of A cross A will be equal to number of A into number of A into number of A. That is number of A cube. This set you can write A cross A. We have written A cross A as A square. Similarly, A cross A you can write as A cube. Number of A cube is number of A the whole cube. So if A has 5 elements, then number of A cube will be 5 cube elements. 5 cube. Now, if A and B are any two sets, can A cross B equal to B cross A? Let us take some example. A is equal to 1, 2, 3. B equal to, similarly, you take 1, 2. 1, 2. Now you can see that A cross B consists of all the pairs taking the first element from the first set A 1, 2, 3. So B, second object coming from second set, that is 1, 2. So the A cross B consists of the pairs like 1, 1, 1, 2, 1, 2, 1, 2, 2, 3, 1, 3, 2. These are the pairs. Similarly, when you write B cross A, you have to consider all the pairs taking the first object from first set, that is B. So you write 1, 1, 1, 2, 1, 3, like that. 1, 1, 1, 2, 1, 3. Then 2, 1, 2, 2, 2, 3. 2, 3. Now, are these two sets equal? We know two sets P and Q are equal if all the elements of P are in Q and all the elements of Q are in P. That is, P is a subset of Q and Q is a subset of P. Then only we say P equal to Q. Two sets are equal if P is a subset of Q and Q is a subset of P. Now here you check whether the elements of A cross B are in B cross A. Of course, some of the elements are there. 1, 1, 1, 1 is here. 1, 2 is here. 2, 1 is here. 2, 1 is here. 2, 2 is here. 2, 2 is here. But 3, 1 is here. There is no 3, 1 here. But instead there is a 1, 3. 1, 3 is not in A cross B. 3, 1 is not in B cross A. Therefore, these two sets cannot be equal. A cross B generally not equal to B cross A. But A cross B can be equal to B cross A. Why here A cross B not equal to B cross? Because A consists of 1, 2, 3. B consists of 1, 2. There is no 3 here. So that pair, such pairs will not be in either of these. So A cross B equal to B cross A if and only if A equal to B. If these two sets are equal, where equal, it would be equal. They would be equal. This A cross B should be equal to B cross A. So we have the result that A cross B equal to B cross A if and only if A is equal to B. Thus we have seen if A and B are any two sets, the Cartesian product of A and B denoted by A cross B is equal to the set of all ordered pairs x, y such that x is in A, y is in B. In a similar way, suppose we have three sets A, B, C. We can define the Cartesian product of these three sets, which is denoted by A cross B cross C, which consists of all the triplets x, y, z such that x is from A, y is from B, z is from C. For example, if A is equal to set 1, 2, B equal to set 3, 4, C equal to set 5, 6, 7, then A cross B cross C consists of all the triplets like 1, 3, 5, 1, 3, 5, taking the first element from A, second element from B, third element from C. 1, 4, 5. Like that, you can write all the possible triplets. You can see that A has 2 elements, B has 2 elements, C has 3 elements, and therefore A cross B cross C will have the elements 2 into 3, which is equal to 12. So there are 12 such triplets by taking elements from first element from A, second element from B, third element from C. Now, suppose we have a set A which consists of the elements 1, 2, 3. We can take the Cartesian product of A with itself, which is denoted by A cross A, which consists of all the pairs by taking element from first element from 1, 2, 3 and second element also from 1, 2, 3. That is, you write A twice, then you write all the possible pairs 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3, then 3, 1, 3, 2, 3, 3. you can see that there are 9 elements in A cross A. This A cross A is sometimes denoted by A square. So number of elements of A square is equal to number of A square. Here there are 3 elements in A and A cross A has 9 elements. Here there are 3 elements, A cross A has 9 elements, that is 3 square elements. In a similar way, you can write A cross A, that is also denoted by A cube, which consists of number of A the whole cube, number of triplets. Now let us see some more results regarding Cartesian product. Suppose we have 3 sets A, B, C. Then what will be A cross B union C? B union C consists of all the elements either from A or from B or from C. That is all the elements like this. This is B union C. And A is suppose another set. Then what is set A cross B union C? We can see that this is equal to A cross B union A cross C. For that, let us take an example first. A equal to 1, 2, B equal to 3, 4, C is equal to 4, 5. Then we know B union C is equal to 3, 4, 5. Now take the product of A with the B union C. You can write A cross B union C is equal to all the pairs taking first element from A and second element from B union C. That is the pairs like 1, 3, 1, 4, 1, 5, then 2, 3, 2, 4, 2, 5. So this is A cross B union C. On the other hand, you find A cross B and A cross C separately. A cross B consists of the pairs taking first element from A, second element from B. That is pairs like 1, 3, 1, 4, 2, 3, 2, 4. Similarly, A cross C is equal to 1, 4, 1, 5, 2, 4, 2, 5. Now from these you can write A cross B union A cross C, which consists of the pairs 1, 3, 1, 4, 2, 3, 2, 4, 1, 3, 1, 4, 2, 3, 2, 4. Then 1, 4 we have already taken, 1, 5, 2, 5. 1, 5, 2, 5. 2, 4 also we have written already. Now this is A cross B union C. This is A cross B union A cross C. You can see that these two sets are identical. A cross B union C is the same as A cross B union A cross C. So we have the result A cross B union C is equal to A cross B union A cross C. We can prove it this generally by showing that these two sets are equal. When two sets are equal, P and Q are any two sets, then P equal to Q if and only if P is a subset of Q and Q is a subset of P. So in order to prove two sets are equal, you need to prove that P is a subset of Q and Q is a subset of P. And how do we show P subset of Q? You take any element in P and show that that element is in Q. That is how we show one set is a subset of another. So here we need to prove first A cross B union C is a subset of A cross B union A cross C. For that, take any x comma y in A cross B union C. This implies x is in A, y is in B union C. This implies x is in A, y is in B, or y is in C, which implies x is in A, y is in B, or x is in A, y is in C. That implies x is in A, y is in B means the pair xy is in A cross B, or x is in A, y is in C means the pair xy is in A cross C. This together implies xy is in A cross B union A cross C. So thus we prove that A cross B union C is a subset of A cross B union A cross C. Now to prove the other implication, that is A cross B union A cross C is a subset of A cross B union C, just reverse these steps. That is, first you take xy is in A cross B union A cross C and go back. You can see that xy is in A cross B union C. So that A cross B union A cross C is a subset of A cross B union. So this implies A cross B union C is equal to A cross B union A cross C. In a similar way, for any three sets A, B, C, we can prove A cross B intersection C is equal to A cross B intersection A cross C. This you can verify by taking example or generally by taking xy in A cross B intersection C and show that that is in A cross B intersection A cross N. And the reverse implication also you prove. Thereby you can prove generally A cross B intersection C equal to A cross B intersection A cross C. Now we will move on to the definition of relation. We will be seeing that relation is a subset of Cartesian product of two sets. Thus we have seen what is Cartesian product of two sets. Now we are in a position to define what is a relation. If A and B are any two non-empty sets, a relation from A to B, a relation from A to B is a subset of A cross B, a subset of A cross B. For example, suppose A is equal to set 1, 2, 3, B equal to set A, B. Now you define a subset of A cross B. A cross B consists of all the pairs like 1A, 1B, 2A, 2B, 3A, 3B, etc. Now you take one of such subsets I am taking R, which is equal to the set of all pairs like 1A, 1B, 2A, consists of only three elements, which is a subset of A cross B. Now this is a relation from A to B. A relation from A to B is denoted by the symbol like this, R colon A arrow B. Another relation I am writing R1 from A to B, 1A, 2B, 3A, 2A. This is also a subset of A cross B and therefore it is a relation from A to B. So a relation from a set A to B is a subset of A cross B. Now as we are writing sets in different forms, relation also can be written in different ways. One is roster form or tabular form we can write. We can write a relation in set builder form, and also using arrow diagram we can show a relation. For example, suppose A is equal to 1, 2, 3 and B is equal to 1, 4, 6, 9, and I am writing a relation from A to B as R from A to B equal to, which consists of the pairs like 1, 1, 2, 4, 3, 9. This is some subset of A cross B. It is a relation from A to B. Now this, I have listed all the elements here as a pairs in the R. So it is tabular form. Now try to write this in set builder form. How do we write the set R in set builder form? Let us see. Now these pairs can be represented by xy, where what is the relation connecting first element and second element in each of these pairs? You verify. You can observe that 1 is related to 1, 2 is related to 4, 3 is related to 9. That means the second element is always the square of 1. So x and y are related in such a way that y is equal to x square, where x in A, y in B. This is the way we write this relation in set builder form. And the same thing you can write by using arrow diagram also. Suppose these sets are A and B consisting of elements 1, 2, 3 and 1, 4, 6, 9 respectively. Then in this relation 1 is related to 1. That is shown by using an arrow like this. 2 is related to 4. 3 is related to 9. This is called arrow diagram. So in these three ways we can represent a relation from one set to another set. Now what is domain and range of a relation? Let us take a relation from A to B with R is equal to R from A to B, which is equal to the set of all like 1 minus 1, 2 minus 2, 3 minus 4, 5 minus 6. Now the range of the domain of R is the set of all first elements of these pairs. We collect all the first elements, that is 1, 2, 3, 5. This is the domain of R. Range of R is the set of all the second elements. That means set minus 1, minus 2, minus 4, minus 6. The set of all first elements of the pairs of a relation is domain. The set of all second elements of the pairs of a relation is range. Or domain you can define such that domain equal to the set of all y, set of all x such that xy is in R, if R is the relation from A to B. Range is the set of all y such that xy is in R. This is the set theoretic definition of domain and range. Let us take some more example. Suppose R is a relation from A to B, where A equal to 1, 2, 3, 4, B equal to 1, 2, 3, 4, 5, 6, consisting of the pairs 1, 2, 2, 4, 3, 6. Now this is the tabular form. You try to write this in the set builder form, which consists of the pairs x, y. You see if there is any relation connecting the first element and second, unique relation. If there is, you can write in the set builder form. Otherwise, you cannot write. Here 1 and 2 are, here 2 and 4 are related, 3 and 6 are related. So the second element is always twice that of the first element. So xy such that y is equal to twice x, 2x, where x in A, y in B. This is this relation. So this relation 1, 2, 2, 4, 3, 6. But remember, there is no 4, 8 here. 4 has no image here. This is called, the second element is usually called image. So here 2 is the image of 1 under the relation R. 4 is the image of 2 under the relation R. 6 is the image of relation under 3. But 4 has no image in B under this relation y equal to 2x. If I write another relation R1 is equal to like 1, 4, 2, 3, 3, 5. Likewise, if you write, it is not possible here, may not be possible here to write a set builder form xy such that y is some expression in terms of x. It may not be possible. Because 1 and 4 are related, 2 and 3 are related, 3 and 5 are related in not in a unique way. This is deliberately chosen. Therefore, this may not be able to be written in the form set builder form. But you can write this using arrow diagram. Now let us take an example. R from A to B defined by set of all xy such that y is equal to 2x plus 1, where A equal to set 1, 2, 3, 4. This is in the set builder form. A is given, B is not given here. B you can find afterwards. Here R consists of the pairs xy, where y is 2x plus 1. That means the image of x is 2x plus 1. So the image of 1 is 2 into 1 plus 1, that is 3. Image of 2 is 2 into 2 plus 1, that is 5. Image of 3 is 2 into 3 plus 1, that is 7. Image of 4 is similarly 2 into 4 plus 1, that is 9. So the range of this function consists of 3, 5, 7, 9, and therefore the pairs are 1, 3, 2, 5, 3, 7, 4, 9, 4, 9. And therefore B is actually a superset of the elements containing 3, 5, 7, 9. 3, 5, 7, 9, that is the range is always a subset of B. Domain is always a subset of A. So here the range is 3, 5, 7, 9. Therefore it is a subset of B, and therefore B can be any set which is a superset of the set 3, 5, 7, 9. Can be equal to 3, 5, 7, 9, or it is any set which contains 3, 5, 7, 9. Now suppose there is a relation like I am showing an arrow diagram here. You have to write its tabular form and also set builder form if possible. A consists of minus 2, minus 1, 0, 1, 2, and B consists of 0, 1, 4, 5. Now this is the relation by it's shown here, minus 2 to 4, minus 1 to 1, 0 to 0, again 1 to 1, 2 to 4. This is an arrow diagram showing some relation, let it be R from A to B, which consists of the pairs. If you write the tabular form, you can see that consists of the pairs like minus 2, 4, minus 1, 1, 0, 0, 1, 1, 2, 4. Here every element in the first element and the second element are related in such a way that the second element is a square of the first element. So this can be written in tabular form, set builder form as xy, where y is equal to x square, because 4 is the square of minus 2, 1 is the square of minus 1, 0 is the square of 0, like that, where x in A, y is from B. This is the tabular form of set builder form of the relation given in this picture, and this is the tabular form of the relation. So if you are given a relation either in arrow diagram or set builder form or a tabular form, we can write the other two types. But set builder form can be written only if you can identify the relation connecting the first element and second element. That must be a very unique relation, must be there. If it is in a haphazard manner, these are associated, then it is not possible to write such a relation like y is equal to an expression in terms of x. If A is equal to set 1, 2, 3, we can define a relation from A to A also. That will be a subset of A cross A. Any subset of A cross A is a relation from A to A. For example, R consists of the pairs like 1, 1, 1, 2, 2, 3. It is a relation from A to A. A to A. This relation, if it is from A to itself, A, then we call this relation a relation on A. A relation on A is the way normally we say. Relation on A means it is a relation from A to A. That's about relation. In my next video, we will be discussing function and some of its properties, examples, etc. Thank you.